All right, so we are starting with this. Like I said, before I get into the notes here, Adam, Omar. So before I dive into the notes, you've probably seen this morning that I put in your friction labs. So you got to see what your marks look like for that. Some of you might have seen that your marks changed drastically, even though your mark was decent. And the reason for that is the only project that was in the term before was your list of 5, which most got 100%. So your mark for projects now went from 100 to whatever percentage. So that's why you saw a drop. What I'm going to do is I'm not going to give you a re-project because I don't want to redo that. However, I am going to construct some sort of additional project you can do over the spring break if you want to do it. So if you're fine with your mark, you don't want to improve anything, leave it as such. However, I will give you an option of a project to do over the break. But be aware, this project I'm still marking as if it is a normal project. So it could bring your mark up. If you get higher than your project average, it could bring your mark down if it gets lower than your project average. So if you're going to do it, don't do a half job. Make sure that you're doing it to the highest extent of your abilities. So I will post that. When did I say that I'm going to prep it? I will post it either on Wednesday or Thursday. So you guys aren't going to be here. This is the last time I see you for a week and a half. So you'll just be able to do that. Yes? Okay. If you remember, let me know. Yes? No, this is optional. So I'm under the belief that over holidays, I like to assign no extra work. That's my policy. I'd rather you have a break so that you're refreshed when you get back. But because of the project, and I realized that there's only one big project in term 3 so far, I wanted to give you a chance to improve that mark. So that's why I'm giving you the option. You don't have to do it. I'm not forcing you to do it. However, if you do it, you need to do it as good as you can. I haven't decided yet. I haven't made the project. So once I have it, you'll see it. Okay, so we are doing the energy unit. Like I said, there are 7 sections. I'm going to cover one of them today. Tomorrow, I'm actually going to cover 2, but the reason for that is it's potential energy and kinetic energy. And these you've both seen before. So it shouldn't be too strenuous for you. Okay, so energy. Energy is the ability to do work. So this might seem I'm using a term that I haven't defined yet, but energy is the ability to do work. And I'm going to also talk about work, so don't worry about that. But this is what energy is. So work and energy are both scalar. So can someone remind me, what does it mean if something is scalar? It has no direction. So it has a magnitude. There's some sort of number associated with it, but there's no direction. So nobody's going to tell you, I've got 50 joules of energy north. Okay, that makes no sense. I have no energy in a direction. And it's measured in 2 things. You can either write newtons times meters or joules, and I'll explain where those come from in a sec. Typically, we use joules, so capital J for energy. Just in general, that's what you typically use. Whoops. I thought there was more on that slide. Give you a sec to jot that down. Kareem, you gonna write this? No? You still gonna pay attention? Not going to pay attention? Oh, okay. I already put that. Okay, so work has many different meanings. So I said energy is the ability to do work, but work has a few definitions. So we can talk about two things with work. Either it is the change in energy. So remember the delta symbol or the triangle, this is just change in. So work is change in energy. And we can talk about any types of energy in this case. Or it is a force times a distance. So these are the two definitions of work. Change in energy, and energy is in joules. Or work is force times distance, newtons times meters. Is this what, sorry? This? Yes, force times distance. So newtons times meters, that's where this comes from. So the question then becomes, which of these equations do I use? Or how do you know which equation you're going to use once you're given a question? So this is something you need to think about as we're going through these problems. Think about, do I use a change in energy, or do I use a force times a distance? So in physics terms, we talk about work being done on an object. So if I'm moving an object, I say I'm doing work on this. So if I take my water bottle and I lift it up, I say I'm doing work on my water bottle. Or if I lower it back down. So for example, suppose I was holding 30 kilogram weight at a height of 1.5 meters. So I am using energy. So let's consider this. Let's say I'm holding two different things. So let's say I've got this box and I've got a pencil. Okay? So I've got two different things that are going on here. And let's say I hold this one steady and I lift this pencil up. Which one do you think I'm doing more work? This one? With the box or the pencil? Pencil? I hear pencil, I hear box. Who thinks pencil? Few people. Who thinks box? Who is undecided and hasn't raised their hand up, which is about 50% of you? Okay, so thinking back to the last slide, what are the two equations for work? Force times distance. If I hold something at a steady height, am I applying a force? No. I sure am. Right? If I'm holding a box, think about the free body diagram. Force of gravity down, I have to apply a force up. So I'm applying a force, however, what's the distance? 0. I'm not moving. So I haven't applied a force across any distance. So in addition to what I said last, if I have these two objects, which one am I applying a bigger force? The box is definitely a heavier object, so I'm applying more force on the box. However, this has a non-zero distance. Yeah. So even though the force is smaller with the pencil, it's times a distance instead of times 0. So in this case, if I'm just holding something at a steady height, I'm not actually doing work. So my muscles, yes, they're doing work. So you can think of someone who's holding a really heavy object. They're doing some sort of work or applying a force. But it's not actually doing work on an object, just on the muscles. So to think of this, you're exerting a force, but your distance traveled is 0. So this is essentially what I was saying, just all written down. So you can think about that. You need to not only apply a force, but you also need to apply it over a distance. Otherwise, you're not actually doing any work. Yep.
So what's the difference between the W of the work and the W of the weight?
Oh, yeah. So W of work and W of weight, they both have the same symbol. So yes, that's going to get confusing. That's why typically I write weight as Fg. So that you can distinguish and say Fg is the weight, but it's written different than work. You'll typically see it written as that. Any questions on this? Okay. So if instead I were to take this 30 kilogram weight and bring it from the ground up to 1.5, now let's consider the work done on the object. So this time I'm actually moving. Instead of holding it at 1.5 meters, I'm lifting it 1.5 meters. So in order to do this, we need to look at the work equals force times distance. And the force in this case, because I'm lifting against gravity, is actually just the force of gravity. So where I've got m times g, that should really look familiar, right? Because we have this, and because we have force of gravity equals m times g, this is our equation. Is this not written on there? If it's kind of intermixed here. So we're gonna, in the little box on the right, second row, this is where you're putting the formula. So we're gonna use that to solve it. So in this case, here are the different variables. I'll give you a sec to write that, and then we're going to calculate it. Confused? So in doing this, I'm not going to write it down. Oh no, I will write it down. I might as well while I'm here. So we didn't actually calculate what this is, right? So what would be the work that I'm doing on the weight? Well, that's really hard to see, but I don't think any of these are going to be better. Nope. Let's just make it thicker. No, it was this one. There we go. So we said the work is mgd, mass times 9.8 times the distance. You have all these variables. I've got the mass, 30. I've got g, 9.8. I've got distance of 1.5. So it's just 30 times 9.8 times the distance, 1.5. What's that? Sure, sounds about right. 441, and what's the unit for work? Joules or Newton meters. Yep, let's do joules. And technically, nope. Technically, it doesn't matter joules, Newton meters. Notice I could do kilograms, meters per second squared times meters. So kilogram meter squared divided by second squared. That works too. You can get some really ugly units, but it doesn't matter. Joules, energy, just remember that.
So here the mass.
M is mass, G is 9.8, or if you're on a different planet, something different, and then height. Depends on what planet you're on. So G all depends on which planet you're on. So let's do a few questions here. So we've got a 10 kilogram pumpkin is moving horizontally at a constant velocity on a level floor. And we're told the horizontal force. And we want to know how much work is done in moving the pumpkin. So we've got two equations for work. Change in energy, force times distance. We haven't really talked about change in energy yet. But since it's a constant velocity, there's no change in energy. So I just want to look at what's the force times the distance. So in this case, we're wanting the work done to move the object. So this force is actually going to be the applied force. So here's where it's going to get confusing, is knowing which force do I use. So in this case, and there'll be a thing that'll pop up, but this one's the force applied. So this one's just 3 times 5, not meters, joules. You know the distance that you're being pushed. You know the force that you're applying on the object. So notice I gave you the mass. Don't need it. Constant velocity doesn't really help us in this question until we get into change in energy. So this is it. Pretty easy when I'm doing it. But again, note I'm using force applied in this. So the force used in this is your applied force, not the net force. So this is in the line underneath where you solve this. You're filling this in down there. So note, use applied force, not net force. So this is in the line that's underneath what we just solved. So if you were paying attention when I explained it, instead of talking to the individuals around you, you would have heard me explain exactly your question. Good. You have me slightly worried. Anyone still jotting this down? So let's try this one. We've got a 3.0 kilogram pineapple being held at 1.2 meters above the floor for 15 seconds. We want to know how much work is done on the pineapple. So, work equals, we can deal with force times distance. So, in this case, what force am I doing onto the pumpkin? Well, if we were to do a free body diagram, if you look at this, it's being held at this distance, so Fg equals force applied, because you're not accelerating. So this force, which is force applied, equals Fg, I'll write this out, which is equal to mg g. We've seen this before. So I have a mass. It doesn't say anything, so we'll assume we're on the Earth. And the distance we're given is 1.2. Just seeing if people are awake. I did something wrong. I'll give you a sec to look. I did something wrong. Yes, I know it's annoying that I keep doing this. But if you can recognize the mistake, this actually helps you in remembering this. Let's go through this step by step. Is my free body diagram correct? Yeah, I'm holding an object. Is it accelerating up or down, left or right? No, so all the forces have to be balanced. So that's correct. Does work equal force times distance? Yeah. And we're doing work on the pineapple, so it has to be force applied. That's correct. I'll tell you that right now. Force applied is equal to force of gravity. So this is correct. Does force of gravity equal m times g? Yeah. Is my mass 3? Yes. Is my g 9.8? Yes. Is the distance traveled 1.2? Is my object moving? No. So I'm applying this force for no distance. So this is a very nice trick question to put on your test. Yes, I like to put it on there. Because you need to think about this. What does this distance mean? What's the distance the force is traveled across? So the distance that you move the pineapple is 0. Therefore, the work done is 0. So this is the exact same with the holding the box, lifting a pencil. Same exact thing. If you're not moving, you are applying this force over no distance. Questions on that? Because this is a concept that's tricky. So just to restate that, no distance means no work done on the object. Again, this is in the little note at the bottom of that box. So you should be looking for, did I actually move a distance? How could I rephrase this question so that my distance traveled is 1.2? What would that look like? Yeah, so I could say a 3 kilogram pineapple is lifted 1.2 meters above the floor. Instead of held, you'd say lift. Or carried upwards. Moved. Yep. Although moved is ambiguous. This question, cross it off. I'm not going to teach you this, or I'm not going to test you on this. If you want to, I'm going to give you a quick teaser for next year, if you're wanting to take something with me next year after you survive Physics 11. So essentially, it's something like this. So you're given something where you've got a force applied. It's now at an angle. So essentially, all you're going to do is something like this, is I need to look at what is the force applied in the x direction. So if you want to know what Physics 12 is like, take this here, add triangles. How do you get this? Well, I know the hypotenuse. I want the adjacent side to the angle. So I just use SOHCAHTOA. This, if you don't like SOHCAHTOA or the sine law, cosine law, don't take Physics 12, because that's going to be everywhere. But now back to what you can do. So we've got a car traveling at this speed. It's brought to a stop while skidding, meaning it's got some friction force. What is the work done on the car by the friction force? So something to note with this. When it says, what is the work done by frictional forces? When I'm doing work equals force times distance, if it says the work done by something, some force, that is the force you are using here. So in general, if it's what is the work done on an object, force applied, in general. If I give you some other specific situation, what's the work done by gravity? It's going to be force of gravity. What's the work done by air resistance? Force, air resistance. So whatever I say, the work done by something, that's going to be your force. So let's calculate this. Yep.
In this question, the distance is 42 meters.
So is that the distance that the force is applied on? If you think about it, so a car is skidding to a stop, so the car is sliding 42 meters. So would that be the distance that the force is applied over? Mm-hmm. Friction force. We need to calculate that. So how can we get this? Well, let's figure out what we got. We've got a mass. Right now that doesn't help us, but we'll put it in there. We've got, what's 61 kilometers per hour? This is my velocity initial or final? So this is VI. And already I see kilometers per hour. You should load kilometers per hour. You always want it in meters per second. So 61 divided by 3.6. This will get us 16.94 meters per second. What else we got? 42 meters. So we got a distance. What else we got? Good. So the number given that's not a number comes to a stop. So this means VF equals 0. Yep. Kinematics always comes back. So it's the very first unit we do. So how does this help us? So if I look at the equation, I want work. Notice I'm telling you my thought process for this, because you're going to get to a question that you have no idea how to get it. And I'm telling you how to do the process for it. So let's start with what we're trying to solve. I want work. I need force of friction and distance. I have distance. I do not have force of friction. So how could I get force of friction? What would be something we could do? So we have the equation for force of friction equals mu Fn. Are we given mu? No, we don't have mu. Are you sure it's F net? I'm getting you to think about what you're saying. Don't just throw something out without being able to back it up. So how could we figure out F net? Well, let's do a free body diagram. So I've got Fg, I've got Fn. These are the easy ones, because it's a car sitting on a surface. What other forces do we have? So it's traveling, and it comes to a stop while skidding. If you're coming to a stop, are you stepping on the brakes or the gas? Brakes, which is going to cause a friction force, not a force applied. So F net is force of friction. But I needed you to think about it. So because of this, F net equals force of friction. Great. So now I can say work is equal to F net times distance. Do I know my F net? I still don't know F net. Okay, so I need to go back and figure out how can I get F net. What's my equation for F net? MA, perfect. So this is equal to MAD, and some of you are going mad right now because I keep doing this. I have the mass, thank goodness. Do I have acceleration? Ugh. Okay, how do I get acceleration? Kinematics. Notice my thought pattern as I go through this. I started with, what do I want to solve for? What do I not know? How could I get it? This. Okay, put that back in. Do I have this? No. Okay, what do I do to get that? Well, it equals this. Great. Do I have all these? No. I have this, I don't have this. And then I need to get that. So notice how I'm working my way down in the thought process. So some of you like to do just easy 2 steps, I'm done. I'm showing you the steps to see, look, you can solve this without knowing a single thing about how to get to the final answer. Just start where you want to go. Take steps. Okay? How many times have you sat on a test and said, Mister, I have no idea how to do this question? I've seen that quite a few. So start with what you want. That'll lead you to what you need to get. So acceleration, I need to use kinematics. So in kinematics, I've got v initial, I've got v final, I've got a distance. So I need to figure out which equation that is. I'll just tell you what it is for the sake of time. It's going to be vf squared equals v naught squared plus 2ad. By now you should get annoyed with me saying this. Do I have everything in this equation except acceleration? Vf? Yes. V naught? Yes. Or Vi? D? Yes. Okay, we can finally solve for something. So 0 squared equals 16.94 squared plus 2 times a times distance, which is 42. So calculate this. What do we get? 16.94 squared divided by 2 divided by 42. I get an acceleration of negative 3.42. Can I have a negative acceleration? What does it mean if it's negative? It's slowing down. Right? A car is coming to a stop, it's decelerating, which means its acceleration is negative. It's in the opposite direction. So yes, we can have negative acceleration. Now because we're dealing with scalars, and we're not indicating direction, but I still need to put negatives in my equation. So this is something new, because we're dealing with scalars. So I have the mass. I now have the acceleration, which is negative. I have a distance. Calculate all of this. Oh goodness. Okay, we get a large number. I'm going to round this. 1.99 times 10 to the 345 joules. Sorry, this should be negative. So in this case, we have a negative work. And this is possible. And you're going to leave your answer as negative. But what does negative tell you in this case? It's related to it stopping. So it doesn't so much have to do with direction, because we're dealing with scalars. Because we can't say it's work in the opposite direction. Yeah. It's part of slowing down. It's not that the friction is more than the speed, but you guys are getting pretty close to it. If you want a hint. It's more to do with your change in energy. Sorry if you can't see that. since work is change in energy, work can be negative. Meaning, I started off with more energy than I finished with. So since work is change in energy, and change in energy is final energy minus initial, so final is smaller than the initial, you can have negative work. It's entirely possible. Oh, I get. You were talking about direction because of what it says on here? Yeah, that makes sense. I tricked you. Yeah. So it is, because you're going in the opposite direction, it gives you a negative change in energy. But that's why I was saying you were on the right path with that. Yep. Yes, you may. Okay, any questions on this? Or anyone still need to write it out? All right, so that is the first section. If you flip over to the next page, you've got the worksheet to work on. Do not do question 5. Yeah, question 5 is the one I said not to do from the notes today.